All right. So no order. Okay. So that means C, the big number always goes first. And then however many we picking is right here. All right. So I'm going to try to do this with the handheld method. I'll probably do one of them like that just because it's a little bit entailed. So we take the difference just like we do for the permutations. And then that's the 4 factorial. All right. So up here, this is going to be 17 factorial, 13 factorial, and then 4 factorial. Now, as far as level of difficulty goes, the combinations is second to the permutations because you got that extra number there. All right. So after you get rid of the big number in the bottom, you still got another factorial to take out. And then the repeated items, the duplicate items, I should say, the one with Mississippi and Alabama and all that, those would be the hardest ones because you can have more than two down there. All right. So up here, 17 times 16 times 15 times 14 times 13 factorial rather than count all the way down. And then down here is the 13 factorial. And then the 4 factorial. Those are being multiplied. So one fraction. So all of these are gone now. Those are 1 now. So then what's left is the 4 factorial down there. I'm going to write it out. Four times 3 times 2 times 1. Okay. So now we can take those numbers in the denominator out any way we wish. Now, sometimes we're constrained and there's only one way to do it. But in this case, 4 goes into 16. That's the only number that's divisible by 4. All right. 17 is not divisible by 3, but 15 is. And then we can go into any even one. I'm going to go to the 14. 2 goes into there 7 times. And now all we got is 1s down there, so we are done. 17 times 4 times 5 times 7 would be equal to 17 times 4 times 5 times 7. So that's 22,380 different ways. Now, let's just see if we did that correctly by doing the calculator thing. All right. So we got 17 faculty members, no order. So we're seeing it, and then we're picking 4. So there we go. We got a match. So I am confident that I have my answer. Okay. All right. So let's see what else we can do. All right. Now, as I had mentioned earlier, I don't know if it was yesterday or today in the earlier class, but a lot of people might ask, well, what use is the non-ordered approach? In other words, if we got a committee of 4 teachers to be chosen from 17, well, we can kind of see that we're treating it as one group, and we don't need to be worried about which 4 it is, because the 4 that are being picked are not ordered. But one of the most popular instances of using combinations is with the lottery. Okay. The lottery, we don't, when you pull out those 5 numbers from that popcorn machine, you don't have to have them in any specific order. If we had to have them in order, nobody's going to win. You see how it's not that often that somebody wins now, and we're just picking the people that have those exact numbers. We're not worried about them in any order. Okay. So the lottery is one of the best examples of this. So let's do this. So what was it? So this is what we call a pick 5. All right. So there's no mention of order in the numbers. Okay. If we want ordered selections, then we have to say that. We either say it by denoting that these 4 are not the same by giving them an office or a position. But with the lottery selections, as long as we got those 5 numbers, it doesn't matter about the order. So what we're coming up with is equals C, and then we're going to do 46, and we're picking 5. All right, and then the way it's gonna be is doing by hand can be a pain in the neck sometimes, and it's hard to tell which ones. So 46 minus 5 is 41. And then we got the 5. factorial. As a matter of fact, this is kind of make that a little bit better. All right, so what's going to happen then is you're going to have up at the top, you're going to take everything from 41 down out. So the only thing that's left is 42. That's the last one that's left. And so down here you got 41 factorial and 5 factorial. All right. So what's going to happen is the 41 factorials will be gone. Let me put a fraction line underneath there. And then in the final rendition of this, so then this is 5 times 4 times 3 times 2. All right, and we can take these out in any way that we want. They will all come out evenly so that we will only have a whole number. So let's see. So 5 goes into 45 9 times. 4 goes into 44 11 times. And 3 goes into 42 14 times, I think. So all these are ones now. And then we can take 2 out of any one that's even. I'm going to take the big number. So this would go 23 times. So everything now has been factored out from the denominator. And the only thing we have down there is 1. And if we've got 1 in the denominator, that means it's going to be a whole number. All right, so what do these multiply out to? So that's 23 times 9 times 11 times 43 times 14. So there are, so there's 1,370,754 pick 5s, provided that the numbers are 1 through 46. Let's do it now and show what happens if we raise that number. Okay. All right.
Wait, did you get that
Now,
by multiplying the 23, 9, 11, and 14?
yes, I did.
All right, because I'm getting 31,878.
Well, you know what? I didn't check it. Let's go back and check it because I'm going too fast. All right. So 46,000. I'm sorry. 46 is the big number. We're doing the C and we're picking 5. And that's the same number. So 1,370,750 pick 5s if we pick from 1 through 46. Okay. Now, let's look at it now with 1 through 56. All right. So then it's going to be 56 here. And we're still picking 5. All right. So I'm going to do it real quick on the calculator, then I'll come back and do it by hand so we can double check it. All right, so 56 now. We're using the C because we're not worried about order here because we just want to have those 5 numbers. We don't care what order they're in. All right, so what does that give us? All right, so 3,819,816. So let me go ahead and do it by hand just to double check it. I went too fast on that last one, and I forgot about doing it. It's a good thing you reminded me, Tori. So let's just go ahead and set it up like this. So it's going to be 56 up top. And then down here, we're going to have the 56 minus 5, which is 51. And then we got the 5 factorial. All right, so this is going to be up at the top. We got 56 times 55 times 54 times 52, 53. And that would be it because everything down from 51 on down is gone because of the 51 down there. I'm going to put it here because we're going to show it's getting striked out. So fraction line. So the 51 factorials are gone. And then here it's going to be 56 times 55 times 54 times 53 times 52 all over. And then it's 5 times 4 times 3 times 2 times 1. The 1 doesn't really add anything, but we put it there so nobody think that we're trying to hide it. Okay, so now so 5 goes into 55 11 times. 52 divided by 4 is 13. 54 is divided by 3. What is 54 divided by 3? You can tell what a number is divided by if you add up the numbers. I'm sorry, the digits. So 3 goes into 54 18 times. And if you don't know that, it's a nice little trick to know if the digits add up to be divisible by 3, then the whole number is divisible by 3. See, like this, 5 and 6 is 11. 11 is not divisible by 3, so 56 is not divisible by 3. 5 plus 5 is 10. 10 is not divisible by 3. So the 55 is not divisible by 3. But 5 and 4 is 9. 9 is divisible by 3. So 54 divided by 3 is 18. And then 2 into 56 gives us 28. So everything down here is gone. So we got 28. So all those numbers just get, oops, it's 18, not 17.
Is this considered the counting principle, or what is this?
No, let me explain that in a second. Let me finish this and I'll explain it. The counting principle is simply where you do the multiplication. Now,
Like the tree
one or more
diagram?
numbers. Yeah, for a tree diagram, but this is the thing is the permutations and the combinations are based upon the counting principle, but they're not like just counting principle, because the counting principle is just when you got numbers, you multiply them. Like if you got 3 groups of items, you multiply the number of items to show how many you would have if you combine them. Let me add this real quick. I mean, multiply this. So then this is 3,819,816, and they match. See that? Good news. So what that essentially means is when we go from n is equal to 46 to 56, the number of ways of picking 5 triples or almost triples. Okay. So by changing that in, did we increase the number of possible picked 5s? And it's almost 3 times as much. Not quite. If it was 3,900, I mean 3,900,000 something, then yeah, but it's pretty close to being. Oh yeah. I'll come. I think that's about all I got. I want to hit a few other little things just to kind of clarify. Because that's a good question you got, Tori, about the accounting principle. I'm going to go back and just kind of accentuate that a bit about the differences. So that's pretty much it for the lesson. Let's go over and look at some stuff. All right. All right. So the counting principle. So we talked a little bit about the probability, and the counting principle is just where we have different groups of experiments. Okay. If we have experiment 1 and it has m ways, and that's just purely a theoretical number, it could be anything. And experiment 2 can be performed in n ways. Then by combining the two experiments, we simply find out how many distinct ways there are then by multiplying the numbers that we have. All right. I'm going to go over to the O20 and get that book. It's got extra stuff in it, problems that I can accentuate with. All right. So the fundamental counting principle is simply finding out how many ways there are to do combined experiments. So to do that, you've got to distinguish. Now, let me just show you on this. Okay, 3 different codes. We if the digits can be repeated. I think we already did this one, but you got 5 digits. So 4 3-digit codes that can be repeated. We're going to just make 3 spots. Now up here, if they can be repeated, then for your first number on your keypad for your code, like a lock or something like that, you can put in 1, 2, 3, 4, 5. Now, if they can be repeated now, then we still got 5. Same thing on the third pick, we still got 5. So there's 125 ways to pick that passcode. Now, if they don't repeat, if they can't be repeated, then what we do is subtract. In this is what's happening in both the permutations and the combinations. You see here, we can do it with repetitions or not, but the nature of the permutations and the combinations is that repetitions or no repetitions is built into it. Okay. The counting principle can be used any number of different ways. All right. As a matter of fact, okay, let me go ahead and just do this. So there'll be 5 the first time. And since you're using one of them, there's only going to be 4 left. And then once you use those 2, there's only 3 left. So 5 times 4 times 3. So then there's going to be 60 ways if we can't have repetition. Now, the notation, the factorial notation, the exclamation point, that is essentially the counting principle in action. The one thing that's different here is that it hinges on cannot be repeated, all right? And the nature of a factorial is, and you can see it here for 2 factorial, okay? It starts at 2, we subtract 1 and get 1 and multiply. 2 times 1 is just 2, of course. For the 3 factorial, the notation means we multiply 3, subtract 1 and get 2, multiply, subtract it again until we get down to 1. And so when we subtract that 3rd time, it's 1. So 3 times 2 is 6. And that happens every time. That's the pattern of the factorial. The factorial notation is setting up this new kind of a possibility to the counting principle, and that is cannot be repeated. You know, they used to, I don't know if you ever see it because I've not bought a deck of cards in a long time, but back in the olden days, you could buy a deck of cards, and one of the, they'd have all the cards that came with it, and then have a couple of jokers, and then they'd have something with like instructions on it. And there was one of the things I remember is it would tell you the probability for each one of the hands, like for a royal flush, for a straight, for just a plain old flush, or for 4 of a kind. And the way that those are calculated, are they calculated with combinations and permutations? Now, cards, because cards don't have any order to the hand, when you pull those things out of that, you're pulling 5 cards out of the deck. There's only one of each card. So once it's in, you're not going to be using it again. It's not going to repeat. So that's instantly why we're putting cannot be repeated here, because that model fits a lot of things, including the one I just mentioned, like cards. All right. So anybody got any final questions? I got one more thing I'm going to show you, and it's a nice little video that explains the difference between the combinations and the permutations, and it explains the difference kind of mathematically and why, and it relates back to the counting principle. So anybody got anything before I start this? All right. All right.
Hey there, what's up? I'm Brett, and today on Math Hacks, we are discussing the difference between combinations and permutations. Combinations and permutations are just one of those topics that's really easy to confuse. And that's because a lot of times in real life, we say combination when we mean permutation. So the difference between the two has to do with ordering. In permutations, the order matters, whereas with combinations, the order doesn't matter. So for example, say I had a combination lock, and the combination to it was 1, 2, 3. Now if it were truly a combination lock, I could walk up to it and put in the numbers 3, 2, 1, and it would open. Or I could enter 2, 1, 3, and it would open. Basically, it would open with any combination of the numbers 1, 2, 3. But as we know, that's not how locks work. They only open when you enter the number in the specific order in which they're supposed to be entered. And that is the definition of a permutation. So the difference between a combination and permutation has everything to do with whether the order matters or not. So we'll be digging deeper into this idea of combinations and permutations in today's lesson. So if you're a little confused by my initial explanation of them, hang in there, because I think by the end of today's lesson, you're going to have a really good grasp for what the difference is. Additionally, we'll be digging into the formulas for each today. So we'll be looking at the choose formula for combinations and the permutate formula for permutations. And I'll be showing you the factorial notation, which is a very common notation found in combinatorics problems. The problem we're going to be looking at today is figuring out how many different 5-card hands can be made from a standard deck of 52 cards. Now, we could jump straight into the combinations and permutations formulas, but instead I want to take you through this logically. And at the end, we will end up with the formulas derived, and you will have a really, really good intuitive sense of how these formulas work, which is really important because in other types of counting problems, you may not always be able to just directly jump into the formula. The easiest way to get started with a counting problem is with a picture. So each of these slots represents a potential card in my hand. When I draw the first card from the deck of 52, I have 52 possible options. So I'm going to put the number 52 in my first slot. Now, once I've taken one card out of the deck has 51 cards left. So for my second card, I only have 51 options left. So I'll put 51 here. Again, now I've pulled 2 cards. So for my third card, I only have 50 options left. I've pulled 3 cards, so I have 49 left, and 48. Now, whenever you're counting the different ways of doing things, you want to use the multiplication principle. So to figure out how many different permutations we have of these, I'm going to multiply all them together. Multiplying this out, I get 311,875,200. And no, I did not do that in my head. I definitely used a calculator for that calculation. Now, this is the number of permutations. Remember in our introduction, I told you that the difference between combinations and permutations is order. In permutations, the order matters. In combinations, it doesn't. So in the problem that we want to solve, order doesn't matter. It doesn't matter if I draw a 2 of hearts first or a 2 of hearts second, as long as a 2 of hearts is in my hand. This means that the arrangement a 2 of hearts, 3 of hearts, 4 of hearts, 5 hearts, 6 hearts is different than 3 of hearts, 2 of hearts, 4 of hearts, 5 of hearts, 6 of hearts, even though they are the same hand. So far we've succeeded at calculating the permutations. Now the question is, how do I get rid of those repeat hands? And to do that, I need to divide them out. This boils down to a sub-problem here. Now I want to figure out how many different ways I can arrange 5 cards. And once I find out how many ways I can do that, I can divide out all those repeat hands from this large number. So again, I have 5 cards, so 5 slots. And I'm just working with one hand of 5 unique cards and seeing how many arrangements I can make. So I have 5 options for the first card, 4 options for the second, 3, 2, 1, just like we did up here. I'm going to multiply these together to get 120. This means that any one hand of cards can be arranged 120 ways. Think about that for a second. That means when you're sitting there
with your cards in your hand and you're trying to organize them, there are 120 different ways you could organize those cards. I want to get rid of all of those repeated arrangements. So I'm going to take our number, our total number of permutations, and divide it by 120, which is all the ways I could arrange any 5 cards. All right, so we still have a really large number, but it's not nearly as large as the number of permutations. So the number of different combinations of 5 card hands from 52 card deck is 2,598,960. Now let's take a look at how this relates to the combinations formula. So here I have this number from multiplying 52 down to 48. And I divided it by this 5 down to 1. Now we're going to do a little bit of clever rewriting to get this into an alternate form. And to do this, we are going to use factorials. Now, 5 times 4 times 3 times 2 times 1 is equivalent to 5 factorial. So I'm going to rewrite that. Now, in the numerator, if I wanted to express this as 52 factorial, I would need to make sure I cancel out everything that's below 48. So that's exactly what we're going to do. I'm going to write 52 factorial in the numerator, which gives me all the integers from 52 down to 1 being multiplied together. I only want the ones down to 48, so I'm going to divide out everything from 47 and down, which I can express as 47 factorial. All right, now what we have here is the definition of the combinations formula. So this can be rewritten as so these are all notations for the combinations formula, and you would read it as N choose K. So in some books, you might see it written as an N on top of a K inside of parentheses, or as a giant C with an N superscript and a K subscript, or as this giant C with a little N in front and a little K after, or as a C with an N and K in parentheses. But they all mean the same thing. They are all the choose or combinations.
In our case, an or.
And the formula for them is N factorial over K factorial times N minus K factorial. And as you can see, that looks a lot like what we wrote up here. So this is the same as 52 choose 5. And when you say it out loud, it makes a lot of sense because I have 52 cards and I want to choose 5 of them. Plugging it into the formula, we would have 52 factorial over 5 factorial times 52 minus 5 factorial. We would subtract these to get 47 factorial. And then we could rewrite 52 factorial as 52 times 51. And because everything's multiplication, this 47 factorial would cancel out with this 47 factorial, leaving us with 52 times 51 times 50 times 49 times 48 all over 5 factorial. And that's really awesome because we have derived the combinations formula. Recall that the only difference between the combinations and the permutations that we had up here was that we divided out all the repeat pairs. So that means our permutations formula is just like the combinations formula, but without this number divided out. So what does that look like? So the permutations formula, which can be written in a variety of notations as well, boils down to N factorial over N minus K factorial, which is just the same as our combinations formula without this K factorial, which removes out all the arrangements we don't care about when we're talking about combinations. To summarize, the difference between combinations and permutations is that in combinations, we don't care about the order of our items. That means that we are going to divide out all of the extra arrangements that are the same combination. And that's why we have this extra k factorial in the denominator. In permutations, we want all of the possible arrangements in every order. And so in this formula, we don't need to divide out the extra arrangements.
As always, there are two really easy things you can do to show your support for math.
All right. So, got any questions? Stick around. Otherwise, I'll see you tomorrow. Bring questions. If you go through that review, I'm going to try to go through. I've already went through it a little bit. I haven't had a chance to work every one of them, but if there's any weird problems in there, I'd like to be able to eliminate them. So bring good feedback, okay?
Hey, thank you.
Bye-bye.
Thank you.
All right. See you.